Okay, now, on the previous tutorial, you saw that when we had the PPC dense overlay of functions on our actual and the true values of women height, and compared this to, I should say, the replications of the true values, which are going to be, I should say, the those that we had from the posterior, I should say, distributions in our model, it showed a plot something like this, which we saw that there are some regions there are very good, I should say, approximations. At some areas, this is not that good enough. We can judge that in overall, it has been a good, I should say, representation. But however, before we just go to the next function that we are just going to do, let's do a quadratic represent modeling of the woman's height. What do I mean by that? Let's get it started. Okay, you know that we call this function stan GLM. That's the thing which we want to do, which comes with in the rstan arm package. And you see that as what we have done before, you see what kind of arguments they are essentials and they are a must that we have to incorporate them into our model. The thing that you just want to do, we just go ahead to start with the formula. We said that for the formula that we are just going to have is going to be this. Previously, in model A, we had the weight as I should say our single variable, but now here I'm just going to say, okay, weight is going to come also as a quadratic term. You saw that also in the regression analysis, in the non-Bayesian also, we said that when you just want to show something, a variable or a covariate, which it comes to a power, either 2, 3, or anything, that we said that normally we do not go above the 2 because there is not any more information to extract after the model becomes cubic. Then we said that we have to just put the I function, which shows that the thing which we have here is going to be taken as a matrix there. And now, then as a result, the formula is going to be ready. And now I'm just going to go to say to the system, to the model, to a function that the data that he's going to jump into to get the information from and build a model is going to be the woman data set. Okay. This is going to be, I should say, all the things that we needed to incorporate. However, as you can see, we can just also specify, for example, the number of the iterations. For example, we manipulate, for example, the priors in the model that we have. But however, let's go ahead to run this model as the way it is. I'm going to call it model underscore. We had model A, B, and C. Let's call that model, let's say, because it's a quadratic term, let's call that model Q. Q stands for the quadratic. Let's execute this line by pressing Ctrl Enter. It says that the object weight not found. Okay, let's go back to see what's the problem with the model that we have had. Okay. Oh, the formula which we have, I forgot to just mention that the height is going to be a function. It was a mistake which I made. It's the height which is a function of the weight. I just want to jump ahead to just write the covariance of the function, and that's the model that we have to run. And you see that when we just run the model, we have this kind of information which shows that from chain number 1 we are going to chain number 2. Essentially, we are just converging into one spot, into our posterior, into our primary space from 4 different directions, which every chain represents one of them. And now when both of them they have been converged, we see that now we have, let's say, we have the 4 chains, we have the total time, and we had, I should say, before the convergence, we had, I should say, we had this warm-up, I should say, sampling in our model. Okay. Now, as long as we have it here, let's go ahead to just go ahead and just run essentially the same thing that we have had. But however, let's go ahead to just write print model Q. And you see that, for example, the model that we have is essentially with some kind of information there, and also we can just write summary of model Q. We want to do a quick, I should say, check up that the model has been converged. We are going to talk about that in future, that the R hat is 1. It shows that the model, as a diagnostic step, the model has converged. Then it's a good step now to just move on to run, I should say, our PP dense overlay. Okay, in order to do that, we just do the same thing. I'm just going to come here as what we have done before. We are just going to go ahead to just write the woman. We're just going to go ahead to just write the posterior. That's the function that we had. The posterior predict from an R stand arm. That's the thing which essentially it draws from the posterior distribution. Then I'm just going to go ahead to just put the name of the object which I had. It is the model. It is called model Q, quadratic model. And the number of the draws that we're going to have, let's say, keep it as the way before. We are just going to make some draws to find the prediction 600 times. And I'm just going to call this one woman. I'm going to store this object, woman posterior, underscore Q. And I'm just going to execute the code by pressing Control Enter and store all the information within the woman posterior Q. The other thing which I can do is that, as what we did before, we can just write, for example, the dimension of the woman. You will see that it's going to be again the same thing. It's going to be 600 rows and 15 columns. Each column represents one observation, woman 1 to woman 15. And also the other thing is that we can just go ahead, just see, for example, the first few lines. For example, the first 2 lines, I'm just going to go ahead, and you see that, for example, for the first rows, which represents the first 3 predictions we had. If, for example, I just go ahead with the Y, you see that for woman number 1, if we have the prediction value for its height as 58.27 inches, our exact value was 58. And now, okay, as long as we are here, we can just go ahead and just, for example, use the same color scheme as before. However, I'm just going to go ahead to do a posterior check, PPC, dense, overlay, and you see that when you just run the help menu, you see that the first option that I have to incorporate inside the function, PPC dense, is going to be the Y, which, if you remember, the Y which we defined before on the previous tutorials, they are representing the actual value of the woman's height. We define it as a woman $ height and store that into the object as Y. And also we have a Y rep, which is going to be the replication of the Y's. What is the Y rep which we have? It's essentially the same object that I created as a quadratic function in our Bayesian model that we had. I'm just going to go ahead to just write a woman posterior Q, and that's all the things which I need for this one. However, because as you saw before, the women posterior Q, it contains 600 draws, which they are represented at each row. In order to make the line, to make the code faster, I'm just going to go ahead to just have the draws from 1 to 40, for example, and with all 15 women, I'm just going to execute the line. Let's see what do I get. And now, you see that the model which we have right now here, it has a better and better realistic, I should say, of the data which we have. Which this model has a very crucial interpretation to make. We saw that previously when we had the model as the one which we had the linear representation of our model. Let me go ahead and just put that the same thing which we had from 1 to 40 and for all 15 women. You saw that when the model, the Bayesian model, it was a linear model. The model that we just produced, it had some, I should say, ups and downs by itself. We saw that at some point, the prediction that we have, the simulation of the data, which is, I should say, the brighter blue, deviates much significantly from, I should say, the true value of the y, which is darker blue. Initially, there are good simulations at the beginning and at the end. Somehow there are some good simulations. However, at the between of those ones, the simulation is drastically bad. You see that there are significant deviations between, I should say, the simulated value, which the brighter blue, and the actual value. However, when we just come here to see that the quadratic model that we created, when we just do our Bayesian analysis as a quadratic model, you see that the model that we have, it essentially has the right, I should say, between the simulated values of the y, which the y represents the woman height, which means that when we simulate the woman heights, we have, I should say, not so much deviations between, I should say, the simulated data and the true and actual data that we had of the woman heights. And they are in much way a neater way than the one which we had in the linear Bayesian regression that we had. Then we saw that this model, the posterior predictive check, has a crucial significance in choosing the right model. Then we ask ourselves, if the model that we have is able to produce the same data, then we said that by just running that one, we can have a very good understanding of how our model is going to simulate the best data, which it was essentially, that was the main purpose of doing this tutorial here. Okay, on the next tutorial, and also you can double check that yourself, when you have a cubic, I should say, representation of the model that you had. I'm just going to do this very quickly. I'm just going to go ahead. In the quadratic one, I'm just come here. I'm just going to copy it. And I'm just going to open. I just want to see the difference if you should have further improvements of the cubic function. I say that the cubic modeling. I'm just going to paste it here. And you see that for the third one, I'm just going to press I. I'm just going to have the weight. It comes to the power 3 because we have the quadratic terms. I'm just going to execute the line. However, it was, let me stop it because it was better cubic. I just put it as the model cubic. Now it's a good time to execute the line by pressing Control Enter, and you see that the model is going through from chain number 1, and it takes a couple of seconds to execute the code and to take, I should say, to finish the sampling. We just started the sampling so far. We had some kind of warm-up to find, I should say, the least, I should say, decent gradient, I should say, of the model. In the parameter space now, the sampling is being done on the chain number 1. I'm just gonna, because it takes some time, I'm just gonna pause the video. When it's done, I'm just gonna go back to continue with the lectures. Now, at this stage, I should say, all the 4 chains, the sampling has been done. It took, I should say, around for, I should say, for the total, it was 31 seconds. And now that we are done with this, I should say, the model cubic, the thing which you wanted to do, I'm just going to go ahead to just create the same function, the posterior predict. Because with the posterior predict, you are just going to essentially do some draws from, I should say, from the posterior distributions. For the object, I put the model cubic. And also, we can say again, the same number of rows. We can say 600 rows. I'm just going to store that into the woman posterior cubic. And it's going to be the name of the object, which I'm just going to store the result of my, I should say, my rows, the prediction. Because you see that, if you remember, the posterior predict, essentially, it do some sampling from the posterior distribution. And when you just put rows 600, it means that the sampling is being done 600 times randomly. And now I have this one there. The other thing which I want to do, as before, I'm just going to go ahead with the PPC dense overlay. I'm just going to go ahead with the actual values of the y, which is the woman height, and also for the y rep, I'm just going to put that woman, that's the object which I created with the cubic model in our Bayesian methods then. And now, because you saw that previously, because the woman posterior cubic, it had, I should say, as before, you can say here, you can say, okay, let's do this kind of things before. With the woman, you see the woman of the posterior cubic, it's going to be again 600 times 15. You can also come here to see that, for example, the head. The first line, I should say, of the woman, I should say posterior cubic. Let's see the first two lines. You see that, for example, it has also almost the same predictions of the woman's height number 1. Let's now, because it has 600 rows in 15 columns, and the dimension of the data sets is a little bit big, and computationally it takes some time, let's go ahead and just select the first, let's say, 40 samples of all these 15 women and execute the line. And you see that the model which you have doesn't change that much compared to the one which we had as a quadratic model. And if you also continue to include a term of the with the power number 4, I should say, in your model, you just extend from cubic model into the quadratic model, then you see that the model doesn't change at all. Then we say that, okay, the quadratic model was the best model in our Bayesian regression analysis, which captures the underlying information from the data to model them. And when we just run, I should say, the posterior predictive check as a dense overlay, we see that this model produced, I should say, replicated and simulated so close data as the one which we had originally in our data system. In the next tutorial, then when we come back, we have some other methods to just run this posterior predictive check, which those ones also give the same information, but with a different, I should say, different style and different graphical representation. See you on the next video.